Okay. Plaskett's binary system consists of two stars that revolve in a circular orbit about a center of mass midway between them. This statement implies that the masses of the two stars are equal. Assume the orbital speed of each star is 240 kilometers per second and the orbital period is 11 and a half days. Find the mass of each star. And they wanted it in solar masses, which is why they have the mass of the sun here. So, here's the picture. This is the two masses. This is their center of mass. I'm just calling this distance r, just because it makes things easy. What else am I going to call it? So I did this problem with forces. So we have force of gravity is equal to ma. Force of gravity, in this case, we're going to use GMM over r squared. And then we have the negative, but we get rid of that negative eventually because I know it's an attractive force. Instead of just doing normal A, I do v squared over r because, one, they gave me v, and also because they're moving centripetally around, like it's centripetal acceleration. They're moving in a circle. And then m is just m. I did this as 2r, again, just because it's the distance between their center of masses, which is 2r, which is just the diameter of that circle. So, multiplying things out, moving things around, you get 4v squared r over g, but we have too many variables to solve this. Obviously, g is a constant and v they gave us, but we do not have r. So, they didn't give us r, but they did give us period, which is that 11 and a half days, if I can find it. It's 11 and a half days. So I just use this equation, which has just solving for r in terms of t, or for t in terms of r, or no, solving for r. And you just move stuff around and you get this, which is why in my next line I have, again, it's just this part of it, 4v squared over g times that vt over 2 pi. And then combining these guys, you get 2v cubed times the period over pi g. Yeah, I just like stupid little substitutions like this always throw me off. I think that's like why I chose this problem, is because of these just stupid little ones that are so important to your understanding of the problem. But I always just mess them up, and I try to use the wrong equation when I do that. I would not have used 2 pi r. I tried to use other stuff. I do not remember what it was, but I could not figure it out for the life of me. Okay, continuing. So now we got this line. Now we go to here. We're just plugging stuff in. Another thing that I did goof was trying to solve this in terms of days. Units for this unit were really tricky just because everything is so big. So I assumed in order to make these numbers kind of smaller, you would want smaller, you would want to use bigger units to, to get used to it. So I didn't think that I should have this in seconds, but you need to have it in seconds because this is in seconds, but that took me a little while to figure out. So one thing I did not do was multiply these days by the 86,400 seconds in a day. I just tried to go about with the 11 and a half days, and it threw me off. But no, you have to convert days to seconds, which is what I did here. And then pi and g are both constant, so it's whatever, you get it. And you get 1.31 times 10 to the 32 kilograms. I did want to stop here because it just, they asked for the mass of the planets, and I found the mass of the planets. But no, they wanted it in solar masses, which is why they gave me this here, which I should have figured out, but I just didn't. So, here's the mass I got. This is the mass of the sun, and then you just divide them to get 65.88 solar masses. Yeah, that's how I solved this problem.